Okay, do you see my slide? Okay. Good afternoon, the audience. Today, I would like to talk about novel curve fitting algorithm based on particle swarm optimization for optical spectrum analysis. Okay, so this is the outline to talk today. First, I would like to talk about introduction and purpose of this research. Second, materials and methods. Third, result and discussion, and finally conclusion. Okay, to start with introduction, I will describe the spectroscopy. The spectroscopy is the study of the interaction between matter and electromagnetic radiation. The spectrum response can be used as a fingerprint for the identify each type of the chemical substance. So a typical spectrophotometer system consists of first, light source, second, optical lens, monochromator to separate each wavelength of the light source using the reflection of through a prism or the diffraction grating. And finally, we detect the signal from the photo detector. And the figure right shows the output of when the photo detector detects the signal. The spectrum response can be used first figure we will see the different spectrum between DNA and protein. The figure 2 shows the using spectrum for the identify protein for in the human trial. And the final figure use spectrum for classify component in the carbon dioxide. In the purpose of this research, we want to curve fitting spectrum correctly and identify depth of the spectrum. Okay. The normal algorithm for the curve fitting have two methods. First, direct search. The method solves the problem by the subtracting every variable and is the possible to the answer certainly. However, this method have the few limitations. First, the user requirements are the minimal, and the algorithm have themselves require the setting for the a few parameters. Second, it's not suitable for the complex optimization problems with the many parameters that cannot finish it manually. And third, is not used many times for the search. And another search is a random search. Random search is another quiet method to carry out the problems. This method is simple and we can random the variable to the represent value suitable for the nonlinear optimization and complex optimization. But the answer may be from the random search is not uncertainty sometimes. So finally we found the particle swarm or PSO that have been put forward for solving complex optimization with the multimodal such as complex equation and the multidimensional problem with the discrete or integrate variable. Next, when we select the method for the curve fitting, then we use another equation for in the PSO. So we use the Gaussian function for the PSO. So, and this parameter in the Gaussian function I will use in the PSO. So first, A is the amplitude of the Gaussian function. Lambda is the wavelength of the Gaussian function. Lambda n is the peak of the wavelength in the Gaussian function. And sigma is the standard deviation of the Gaussian function. N of is the number of the function we use. So next slide, when we create the equation, right? Next step, we will get the new parameter we call the model. So the model is the summation of the Gaussian function, and the model we use the evaluate with the 55 variable to the predict spectral response. The coefficient spectral response accuracy for the each set of the 55 variable, and assesses using the R square. Compare the experiment spectrum with the model spectrum, and we will get the optical function. So when we will go the next step, I want to the two words. When the objective function get the minimum value, we will call the global minima, and if the objective function is not minimum value, we will call the local minima. Okay, let's move on to the how to the PSO work. I assume to the 30 particle on the grid, and I give the yellow particle is the minimum value, I call the global minima, and the other particle I call the local minima. So then the particle know which one is the global minima. The local minima will move to the global minima, but the velocity of the local minima depends on distance. If the particle who is position is farther away from global minima, will move faster velocity, like this in the animation. So the other hand, if the particle is closer to the global minima, the particle will move at the slower velocity. Okay, and this is show the new interaction. The particle will move to the global minima, until the particle will move until the closer the global minima, and they will end the interaction. So next, when we create the PSO and select the method, next step we will use the sample processing. We use DI water, ethanol, ferrous chloride, and golden film. And another step, we will measure the spectrum from the sample from the standard spectrophotometer, and give the signal to analysis based on particle swarm. And this slide show my result when the measure the DI water. So the blue line show the transmission spectrum from the standard spectrophotometer, and the red dot is show the PSO part of PSO curve fitting. So the PSO curve fitting is the summary of the 5 Gaussian. So this will show the Gaussian in you see that? Okay, you will see the 5 Gaussian is the show in the figure, and the red dot will show the R square is 0.8253 for the R square of the PSO. Another result is the external, and the blue line show the transmittance spectrum external. So when we use the PSO port, you will see this. And PS when you see just 4, right? Because the another one is have the lower amplitude. So we will give the R square from the PSO of the external is 0.5910. Another result is the fluorous chloride. So the blue line is the transmittance from the standard spectrophotometer, and the red dot is the PSO curve fitting. So when we use the 5 Gaussian to the plot the PSO, we will give the R square is 0.6101. And the last one of the results, we use the golden film, and this slide show the transmittance of the golden film, and the red dot is the PSO curve fitting too. So you will see the 5 Gaussian is a very deconvolute with the PSO, and you will give and they give the R square is 0.995. It's very higher R square. So the conclusion in this research, we success for the curve fitting for the sample with the PSO. Second, the R square of the water is 0.8253. Ethanol is the 0.5910. And the last, the fluorous chloride is the 0.6101. And the last one, the PSO port will give the R square is 0.995 at the single peak at 36.44 nanometer. And thank you for the attention. So any question? Hello?
Okay, good. Okay. Comes the questions.
Okay.
Okay. Is there any questions from the audience? Please throw your questions to her. Okay. And
okay,
what are you going to do further about spectrophotometers? And the other questions. Okay, the first questions, what are you going to do further about your photometers based on your fundamentals here to use the sorry, it's about to use the software, the PSOs to analyze your spectrum. And the other questions, what will be difference from another kind technique, like to use the curve fittings or to use the another techniques? What will be difference from that?
So I listen the first question, but I will ask the second question first. How the different, right? So in the PS also is can identify the peak and dip if we use the PSO. If the another curve fitting, it can ask the yes, they can tell the peak and dip, but we PSO develop the develop to the pot or curve to the correctly more than the another curve fitting. And so you repeat the first question again.
The first question. Okay. The first question is about what's the further works that you're gonna do in the next steps after you have the PSO analysis. Okay, how can they use it?
When we will use the PSO when we curve fitting with the another part of the, or we will use the sensor field. So I think it's very profit when we use it. I think it will can identify the components of the chemical or substance when we use the PSO. Yeah.
Okay, thanks. Any questions from the audience? Hi there. All right. If there are no questions, so we're gonna move to the last presenters. Thank you.